I'm helping out with a couple of problems on the second semester review, sheet number 3. And I'm going to be working problems 3 and 4. And number 3 is an example of translating inverse variation. And hopefully you remember that when we talked about inverse variation in general, it looks like this. Y equals some constant we call k divided by x. We're getting a little more specific to this problem. It's like we're taking the parent inverse variation function, which would be y equals 2 over x. But you'll notice we've included a little bit more in with this parent function, and this is what is known as a translation or a shift or a move. It's like taking the parent, y equals 2 over x, and adding 3 in the denominator like this to the x is the same way as saying move the parent 3 places to the left. And out here to the right by itself, this subtracting 2 indicates that we're going to take the parent, in addition to moving it 3 to the left, we're also going to shift it 2 places down. Okay, so since we're going to be moving 3 left and 2 down with this parent function, these two movements, 3 left, indicates that now, instead of having a vertical asymptote, which would be the y-axis for the parent, now we're going to have a vertical asymptote, which is x equals -3. Okay, so my graph of the parent, y equals 2 over x, which would have been bound here and here. Now, moving 3 places to the left makes my vertical asymptote shift and become x equals -3. And the shift of 2 places down, if I were graphing the parent, I would have a horizontal asymptote, which would be the x-axis. But now that I'm shifting 2 places down, I now have a horizontal asymptote, which is the line y equals 2. Okay, so here is the way we're going to draw this graph. I'm going to make a table for the parent to make the math pretty easy. We're going to choose both positive and negatives of really 3 numbers. But when we plot these points, we're going to treat this intersection of these 2 asymptotes as the new origin. Okay, so the shift left 3 and down 2 basically has already been taken care of by these 2 new asymptote lines. And so now all we have to do is come up with a pretty simple table, and we'll plot from here. This is our new 0, 0. All right, so remember, we can't use 0 for x, can't divide by 0, but we could use 1, and if we let x be 1, we get y is 2, and the -1 would give us -2. So I'm just going to say it like this. Either +1 gives me +2 or -1 gives me -2. Okay, we can do something similar with 2. If we let x be 2, we get y is 1, and that's also true with -2, you get -1. And then you can do anything you want, but I'm going to go with 1/2, because 2 divided by 1/2 is the same thing as 2 times 2, which gives me 4. And remember, I'm doing both the positive and the negative because these inverse variation graphs come in 2 branches, and to make sure I get both, I need to always plug in both a positive number and its opposite. Okay, so let's start plotting. Again, this is my origin from which I'm going to plot points, and I'm going to plot the point 1, 2, and then 2, 1. 1/2, which would be here, and then 4. And that's one of my branches. Okay, just following the asymptotes. And then we'll do the same thing with the negatives. So again, starting here, -1, -2, -2, -1, -1/2, -4, and this is the other branch. And that is the graph of number 3, which represents a translation of an inverse variation function. Now number 4, some people confuse number 3 with number 4. Well, notice number 4 is not inverse variation. If it were, there would just be a constant in the numerator by itself. That's not what we have here. So this is just a basic rational function, and when we get our eventual table of values, we're going to plot from the origin just like you always have done. This is not a translation where we're going to come up with 2 new asymptote lines from which we're going to plot. We're going to treat that as our new origin. All of our points, when we come up with our points in just a minute, they're all going to be plotted from 0, 0, the original origin. Okay, so for rational functions, there is typically a place where we're not going to be allowed to graph. Those are numbers that plug in for x that would make the denominator 0. To find out what those numbers are, we need to do some factoring. So the numerator doesn't factor, but we can factor the denominator as x plus 6 times x minus 3. And this makes it easy to see the numbers that if we plug them in for x, we would get 0 in the denominator. And these represent points of discontinuity. Numbers on our graph where x is those numbers, our graph really cannot flow through those because those numbers represent 0 in a denominator. Okay, so now we need to name these. These 2 numbers represent either vertical asymptotes or holes. Well, the -6 represents a vertical asymptote because it only makes the denominator 0. That's it. Contrast that with the number 3. Not only does it make the denominator 0, we've already discovered that, but it just so happens that it also makes the numerator 0. And that is the definition of a hole. Now, let's see if we have a horizontal asymptote. If we do, then something like this will happen. The degree of the denominator, which we can see here is 2, is bigger than the degree of the numerator, which is 1. And whenever this situation happens, the degree of the denominator is bigger than the numerator. The horizontal asymptote will always be the same line. It's the line y equals 0, which is another way of saying the x-axis. So this line is going to cause a break in our graph. It's going to cause, it's like a fence. If my graph starts off down here, it can only go up as far as that line. All right. Now, we also have this vertical asymptote we've already discovered as -6. So we need to draw a vertical line at x equals -6. Okay, and that causes breaks, or it causes a break. It causes my graph to not flow continuously. So now, not only is my graph, for example, if it starts down here, not only can it not go above this line, but it also can't go to the right any further than this line. And if it's up here, then it cannot go below the x-axis and it can't go to the right. So this, it's like fences. The big question is my graph going to be up in this area or is it going to be down here? It can't be both because it can't cross that x-axis. And the same thing is true over here to the right. This is kind of like a big divider. To the right of x equals -6 is my graph up here. or is it down here? Well, the way to find out is to just pick a couple of numbers, one number on either side of this vertical asymptote. And I usually just go to the nearest numbers on either side of that vertical line. And we're going to eventually plug them in to our factored form. But let's make this process of plugging in a little bit easier. And so when you get to the point when you're ready to make the table, you should always cancel. Notice that these x minus 3's cancel, and it makes it a lot easier to plug into this rational expression because I'm only plugging one number in for x. And we're going to see what comes out for y. Okay? So let's just take, for example, we can do any number we want to the left of x equals -6. So let's just try -7. Okay, I'm going to put -7 in for x, and when I do, I get -1. Okay, well that tells me all I need to know about what happens to the left of x equals -6, because if that point is on my graph, and we just proved that it is, then all the other points to the left of x equals -6 have to be in this area. And we're always approaching these asymptotes going to the left and to the right. And so that's one of the branches. Okay, well let's see about the other side of this big divider, this vertical asymptote. So let's try -5. If we put -5 in here for x, we get +1. Okay, well that tells me that on the right side of x equals -6, this curve stays above the x-axis, approaching forever. Okay, so I'm approaching going up, and I'm approaching the x-axis coming down. Okay, so we're pretty much done except for we haven't graphed x equals 3 as the whole. Right now we're saying that it's okay for my graph to go through x equals 3, but that's not possible because x equals 3 means we have 0 as a denominator and we can't divide by 0. So our graph has to show that 3 is not allowed as an input. 3 is not, x equals 3 is not part of this graph. So where x equals 3 on my graph, I'm going to put a little circle to indicate that we're jumping over x equals 3. X can be any other number besides 3 and beside -6. We just can't let it be 3 exactly. So that's what this graph now tells us. Okay, and that is the completed graph for number 4. Starts with factoring, find the points of discontinuity, name them, graph the vertical and horizontal asymptotes. You can save the whole until you've actually got something graphed. And then you're just testing what happens on either side of this vertical asymptote, and you can pick numbers on either side to plug into the canceled factored form to make the inputting a lot easier. And so I hope this helps you on the 2 graphs, numbers 3 and 4, on semester review number 3.